Welcome to the Tectonic Hazards revision session. This is going to cover the basics of the unit. So case studies, for example, Eyjafjallajökull and Nyiragongo, you're going to have to revise yourself, but I will put some resources up into the Google Classroom for you to do so. Now what we're going to focus on is the structure of the Earth, the location of tectonic hazards, living with natural hazards, the different types of plate boundaries, and how to reduce the risks. Starting with the structure of the Earth. As you know, our Earth is made up of 4 layers, and those are the inner core, the outer core, the mantle, and the crust. Starting with the inner core, it's a solid made up of iron and nickel. It's highly radioactive, and it's what gives the Earth the magnetic pull that we see. It's up to 5,000 degrees centigrade. So it's extremely hot. Moving out from that, we have the outer core. It's also made of iron and nickel, but it is molten, so it is a liquid form of this iron and nickel. It's also very hot and is between 4,000 and 5,000 degrees centigrade. Coming even further towards the surface than that, we have the mantle, and that's the thickest layer of the Earth. It is extremely hot and is formed of a molten or semi-molten liquid rock called magma, and it's that magma that we then see become lava as it ejects from a volcano. Now we have convection currents happening in the mantle, and that's what drives the movement of our tectonic plates. We'll talk about the convection currents in a little while when we talk about our plate boundaries. The best way to describe the mantle is that it is kind of like a thick, gloopy porridge with kind of like that little bit of crust. So the closer you are to the hot outer core, the more kind of more liquid it is, and the more molten it is, and it flows a little bit better compared to up by the crust, where it's a little bit more solidified. Moving out to the crust, it's our thinnest layer of the Earth, and it's fractured into lots of different tectonic plates. Now there are 2 types of crust that we see, and the first type is oceanic crust. Now this is thin, it is more dense, and it is made of basalt. Our second type of crust is continental crust. Now continental crust is pretty much the opposite. It is thick, it is less dense, and it is made of granite. Now our oceanic crust is between 6 to 8 kilometers thick, whereas our continental crust is between 30 to 50 kilometers thick. It's these different types of crust that cause the 4 different plate boundaries and what happens at them to occur. So let's have a look at plate boundaries. As we know, convection causes our plate to move. Now convection is that movement of heat in a cell formation. It's very similar to the global atmospheric circulation system, which forms our Hadley cells, which we've seen before. So our inner core heats up the Earth and causes the magma in the mantle to rise. This then moves towards the surface, where we see our plates on top of the mantle, and as it rises, it kind of has more energy and it flows up. It then cools down nearer the surface, kind of drags our plates along with it one way or the other, and then cools and starts to sink back down towards the core. That then kind of flows back, and the whole process starts again, exactly like you'd see in convection in science, or that you'd see at the equator with the rising warm air in our Hadley and Ferrel cells. Now there are 4 types of plate margins or plate boundaries. We're going to use the term boundary, but be aware that the term plate margin means exactly the same. The first type is a constructive plate boundary, and this is where we have 2 plates moving away from one another. So they're moving in 2 different directions, pulling apart. Now this then allows magma to rise up to the surface, causing our kind of flat shield volcanoes that we see. Also, as it's moving, we see these kind of movement causing slight tremors and earthquakes. Now the shield volcanoes are caused by this flowing lava, the kind of slow flowing, runny lava, and it is then this which forms our new land. A great example of our constructive boundaries cause our mid-Atlantic ridge that we see. Now the diagram for a constructive boundary is really simple. You need two blocks, as you can see on the screen coming up now, one pulling to the left and one pulling to the right. You can then have the convection cell underneath them if you wish, and I would always do an arrow coming up to represent the magma rising to the surface, causing our layers of our shield volcano to be formed. Now if you are forgetting these, I'll put a link to Mr. Butt's tectonic disco that we've looked at before, which is a great way to remember them. Our second type of boundary is a destructive plate boundary. And what happens is we have two plates moving towards one another. Now, these two plates can be an oceanic and a continental plate, where they move towards each other, or it could be an oceanic and an oceanic plate moving towards each other. And what happens is one of these plates is forced under the other. Now, how that is decided is it's all down to whichever plate is the denser. So where we have an oceanic and a continental plate, we would see our oceanic plate being forced underneath the continental plate in a process that we call subduction. And this then starts to create friction as it's being forced underneath. This friction is then released as an earthquake. As this sinks down underneath, it forms a deep ocean trench, very similar to the Marianas Trench. As our oceanic plate is forced underneath, it starts to melt in the hot magma of the mantle, and this magma then starts to rise up through cracks in the other plate, causing our volcano. Now this is more of a steep-sided composite volcano as opposed to our low-lying flat shield volcanoes that we've seen at a constructive boundary. To draw our diagram, you need one thinner plate that is curving slightly downwards, as you can see coming up on the screen right now. And then you need one thicker plate that is moving towards it, which is less dense. So this would be our continental plate that I'm just drawing now. The arrows are showing you which way they're moving. Remember that a diagram is absolutely brilliant to use in an exam question. It's always good to recognize these as well. I'm going to highlight in red the more dense oceanic plate, and I'll highlight in green the less dense continental plate. And so you'd see the magma rising up through the cracks in this green plate, causing our composite volcano. So remember, we get earthquake and volcano at here. Our third type of plate boundary is called collision. Now this is again two plates moving towards one another, but it is only two continental plates. It only ever happens with two continental plates. So as they move together, they crash into one another and they force each other upwards, kind of crumpling and folding, pushing themselves upwards. And this causes a landform known as fold mountains. The Himalayas is the greatest example I could give you of a fold mountain. Now, no volcanoes happen here because there is no magma coming to the surface. It is only earthquakes that occur here, and they create fold mountains. To draw this diagram, you'll see I'm doing one plate moving in from the left to the right, kind of bending upwards slightly, and another coming in from the right to the left, and you'll see the two meeting and forming our fold mountain range. So it's a little bit wrinkly and bubbly. You'll see this displayed in many different ways, but it always looks very similar to this, where you then see kind of like the halfway point in the middle forming our folds. Okay, hope that's nice and clear. Remember, that's two plates coming together, only ever two continental plates. Our final type of boundary is a conservative plate boundary. Now, this could be either type of plate. It could be oceanic and oceanic, continental and continental, oceanic and continental, but it's where these plates are moving past or alongside one another. Now, this can be where they move in the same direction or in different directions. The San Andreas Fault on the side of California, where the Pacific and the North American plate are moving alongside each other in the same direction, is the best example of a conservative boundary. And as they move against each other, they rub, they kind of catch and drag, and it's what we call a slip strike, where they kind of slip together, strike and kind of knock off, and they form a lot of pressure as this happens, which is released in an earthquake. So we see very violent earthquakes at a conservative boundary because these are so close to the surface. Again, we don't see any volcanoes. Now the diagram is you need two plates next to each other, and then you can do them either in moving the same direction or moving in different directions. As you can see here, I'm doing mine moving in different directions, but they're going past one another, and that friction would build up along the edges. Now we're going to discuss the location of our tectonic hazards. We're going to start by talking about the location of earthquakes. Now, earthquakes occur along our plate margins, so alongside our collision, conservative, destructive, constructive. They're all happening along pretty much all of our plate margins. And there are lots along the western side of South and North America, and there are lots around the Pacific, kind of following along the plate margins there. Lots along the eastern coast of Japan, and lots around the Indonesia area. So remember, this is all happening because of where these boundaries are. Now, we can have some of these earthquakes occurring at different places that are not the result of a plate margin, and that's where it's usually down to human activity such as fracking or mining. Volcanoes, these occur in long belts, usually following our plate boundaries again. Now remember, we don't have them happening at every plate boundary because, for example, conservative and collision, there is no magma reaching the surface, so there's no volcano. Okay, so for example, around the Pacific, we see the Pacific Ring of Fire. Now we do sometimes see volcanoes not at a plate boundary, and this is what we call a hot spot. It's caused by an intense area of radiation in the Earth's core, causing the magma to rise to the surface, where particularly thin crust is at the surface, and this magma is able to break through, and the Hawaiian Islands are the best example of this that I could actually give you. So why do people live in tectonically hazardous areas? Well, there are a couple of reasons. And the first reason is that there is more fertile land from the ash deposits of volcanoes. Now, this means we can grow more crops, and it makes it a much better place for farming. Second reason, precious materials and minerals are brought to the surface by eruptions. We can use the geothermal energy from the magma in these volcanoes to create cheaper and more reliable renewable energy sources. People love these dramatic landscapes that our tectonic processes cause. For example, Iceland. So tourism is a big draw and it employs a lot of people. People may not actually be aware of the risks of a tectonically hazardous area. So we might see people being uneducated and not actually knowing what the risk is. These hazards don't happen all the time, so people may not actually think that they are a big impact on their life. Poverty is one of the biggest causes where people don't have enough money. They've got other concerns such as finding enough food, water and a safe place to live, that they aren't really that concerned about the tectonic hazards that are happening. And they're often located along our trading ports or along coastal areas as well. So using Iceland as our example, there's roughly 320,000 people living in Iceland, and over 1 million people visit each year for tourism. So we can see that it's actually a huge business and provides Iceland with a large amount of its income. So they kind of minimize the risk there. They don't see that it's actually a big problem due to the scientific monitoring that we're going to talk about in just a moment. So that definitely allows the tourism to outweigh the worries and the risks. So for example, the geothermal energy, nearly 90% of Iceland uses geothermal energy and the hot water, and it actually is a huge impact on 25% geothermal energy, but 90% of their hot water comes from this geothermally heated water, which is brilliant. And much of the rest of their energy comes from the natural renewable sources as well. A huge amount of people visited Eyjafjallajökull around Iceland after the eruption in 2010 that we've looked at, which is another great reason that we see a lot of this tourism occurring in the area. Okay, we're going to talk about how to reduce the risks of a tectonically hazardous area. So there are 4 different types or strategies to reduce the risk. We have monitoring, prediction, protection, and planning. We're going to start with monitoring. Now, monitoring is where we use scientific equipment to detect the warning signs of an event. For example, for a volcano, they are closely monitored by scientists to kind of allow us to see when the eruptions are going to happen. And this allows us to evacuate or kind of prepare for this eruption. And these includes different types such as remote sensing, where we use satellites to have a look at what's going on around the land around the volcano. We can look at seismicity, so we use seismometers. We can look at the hydrology, where we look at the gas content in the water surrounding the area. And we can look at the gas emissions that are coming out, just to name a few. Now, we can unfortunately not really monitor earthquakes that much. It doesn't really work due to the fact that earthquakes don't have that many warning signs. There's a little bit of evidence that we could look at the water pressure to give us a small amount to look at, but it's not really a reliable way to do it and predict an earthquake. So unfortunately, monitoring doesn't really work for earthquakes. Our next type of management strategy is prediction. And that's where we use historical evidence to monitor, to predict when and where these hazards may occur. Now, we use the monitoring strategies that we spoke about just now to do this for volcanoes. And, for example, the scientists in Iceland were able to use these monitoring strategies to predict the AQA GCSE eruptions for March and April of 2010 pretty well. Unfortunately, prediction doesn't really work with earthquakes, again, as they don't give off very many warning signs. What we can do, though, is we can use prediction to have a look at areas that are prone to earthquakes and use this to think, oh, they may be due one pretty soon, but it's unfortunately not reliable. Our third strategy is protection. This is where we design buildings that will withstand the hazards. Now, for volcanoes, there's very little we can do to protect the buildings against the volcano, but we can use strategies such as earthen embankments or using small explosives to create channels to move the lava flow away from the high value land. But earthquakes is where protection comes in absolute crutch. Now, we can use earthquake resistant design. Not earthquake proof design. We cannot make a building completely earthquake proof, but we can make it earthquake resistant. So what we can do is we can have different types of design which will allow our buildings to withstand the force of an earthquake. Now, this can include shatterproof glass in the windows, so that they don't shatter everywhere when they break, much like a shatterproof ruler. We can have rubber shock absorbers in the ground. We can have rolling weights on the roof to counteract the swaying, and we can have reinforced concrete and steel structures to help the building sway and move with the shaking. Regular earthquake drills are also a great thing that we use for protection, so that people know exactly what happens when an earthquake occurs, as is having an outside area that people can gather in away from the tall buildings. Now, our final type of reducing risk is planning, and this is where we identify and avoid the places most at risk. Now, for volcanoes, we can use this to create the high value land, and we can look at exactly what's going to happen, and we can create a risk map. So we can look at the high value land and where is most at risk, and we can use this to plan our response to evacuate certain areas. For earthquakes, maps can be produced to show the effects of an earthquake or identify the areas that are most at damage. Again, high value land such as hospitals and office blocks. And this can allow us to move population out of vulnerable area. Now, that brings us to the end of our tectonics revision section. Now, I'd like you guys to go away, look over the research projects that you did last lesson, look at and have a look at the different revision resources that I've placed in the lesson. Okay, so have a look through those. Use your knowledge, use your internet resources, use your revision guides if you have them. And good luck. The assessment will be in a Google form in lesson 3 for this week. Good luck.